All right, so let's continue our discussion of waves and sound by finishing it with a discussion of musical sounds. So, a musical sound is produced by creating a standing wave. So, just think about taking a rope and shaking it up and down. When you look at that rope, it looks like the wave is standing still. And so, what's happening is you send a pulse down and you send it down at a frequency so that it hits the so you send down that pulse, and it travels down, hits the other side, and then it bounces back in such a way that the bounce back wave is 180 degrees out of phase with the wave that you sent down. And so it looks like this, and you can see that this standing wave, where it's at maximum amplitude, we call that an antinode, and where the reflection cancels out the wave that's sent down is called a node. So here there is, this is absolutely a type of destructive interference, which means that you could theoretically put your fingers right at this point and it will not disturb the transition, the wave at all. The wave would still go. But if you put your finger over here on any part, anywhere else, the energy will be destroyed. So let's talk about standing waves that form on things like guitar strings. So let's take a length of string, L, and let's get it to vibrate at its lowest frequency. So at its very lowest frequency, it just has one antinode. At the second highest frequency, called the second harmonic, so this is the fundamental or first harmonic, and this is the second harmonic, the third harmonic, the fourth harmonic, and so forth. The fundamental has one antinode and two nodes at either end. And the only way this can form is so that there are nodes on the end, because this is a string that's tied off at each end. And so the only waves that can form are waves that have a node on each end. In other words, an antinode, you could not have something that looks like this. That's not going to happen, okay, because the side is tied off, and so it has to form a node there. So the second harmonic has two antinodes, the third has three antinodes, the fourth has four antinodes, and so forth. So now let's look at, you notice that the distance between crests is not the same for these, right? As a matter of fact, this crest would be all the way over here. So look at this. As you go up in harmonics, you get more antinodes, which means the wavelength decreases. And in fact, if you were to look at this very first thing, this is a complete wave right here. This is only 1/2 of the wavelength. This is 2/2 of the wavelength. This is 3/2 of the wavelength, and this is 4/2 of the wavelength. So you can see that as you go up, you can get more and more wavelengths in that same length of string. So in the fundamental, it's got half. The length of the string is equal to half of the fundamental wavelength. At the second harmonic, the length of the string is equal to 2 over 2/2, or that just goes to 1. And for the third harmonic, the length of the string is equal to 3/2 of wavelength 3. At the fourth harmonic, the length of the string, that same length of the string, contains 4/2 of whatever that new wavelength is. So there's a trend here. And remember, too, that the frequency that can form on this is going to be equal to whatever the speed of sound is divided by the wavelength. So if we're talking about frequency 1, the wavelength, the frequency 1 is equal to whatever the speed of sound is divided by whatever the wavelength is at that frequency. Well, if I rearrange this equation here for wavelength, I get wavelength is equal to 2/1 times L. So if I plug this in, V all over 2/1L, or 2L, right? For F2, it would be V all over, if I rearrange this, it's 2/2L. I'm just going to 2/2L or 1L. And then over here, for F3, V is going to be equal to 2/3 L. So what we're seeing is there's some kind of relationship here. It looks like there's some kind of relationship. And it turns out that the general formula to find the frequency is related to this formula here. And I can give you a generic formula for any harmonic, right? And remember, the number n is the number of the harmonic. So F at any harmonic is equal to n times V all over 2 times L. So if I want to know the fifth harmonic, it would be 5 times 331 divided by 2 times whatever the length of the string is that you're using. So let's do an example. So first of all, I will remind you that for a wave on a string, the velocity is equal to the tension force divided by mu, or mass per unit length, divided by, so if I plug that velocity in, right, into the frequency formula, it would look like this. 1 meter string, so that's my L, has a mass of 200 grams or 0.200 kilograms. So mu is going to be 0.200 kilograms divided by 1 meter, or 0.200 kilograms per meter. We'll need to know that. And the tension force is 200 newtons. What are the first 3 harmonics? Well, F1 is going to be 1 times, let's find the speed of the wave. So the speed of the wave is going to be equal to the tension force, which is 200 newtons, divided by the mass per unit length, 0.200 kilograms per meter. Take the square root of that. So 200 divided by 0.2, and then we take the square root of it, is 31.7. So the velocity is 31.7 meters per second. So I am going to plug into my general formula here. Fn equals Nv all over 2L. 1 times 31.7 divided by 2 times 1 meter. So 31.7 divided by 2 is going to be 1585 or 9. Yes, 15.9 hertz. And F2 is going to be 2 times 317 meters per second all over 2 times 1 meter, which, if you notice, this number is the same, right? So really, it's just 2 times F1, which would be 31.7 hertz. And F3 would be 3 times 31.7 meters per second divided by 2 times 1 meter, or simply 3 times F1, which would be 31.7 times 3, which is 95.1. So if we go back to our original picture here, this one would be 31.7 meters per second. I'm sorry, 15.9 and 31.7. My bad. 15.9 hertz, 31.7 hertz. And then the third one would be 95.1 hertz. And the fourth one would be 4 times 15.9, whatever that is, right? All right. So what happens when we're talking about instruments that are made of wind instruments with pipes? Well, we have two kinds of pipes. We have a pipe that's open on both ends. So this would be like a flute, clarinet, a saxophone, anything that has a reed on it, or anything that's a tube that you blow over. It is not a brass instrument like a trumpet or a baritone or tuba. So it turns out that the types of waves that can fit on these have to have antinodes at both ends, because there's nothing pinching it off. But it turns out that the relationship is still the same. So when N is 1, so let's just draw a wave here. So if you think about it, this area here is half the wavelength. So 1/2 of wavelength 1 equals L. And here we have at N equals 2, 2/2 of wavelength 2 equals L. And for N equals 3, we have 3/2 of wavelength 3 equals L. So what I'm saying is that the trend is the same. And so what you're going to find is that to find the frequency that can form in this of any harmonic, it's going to be NV of sound all over 2 times the length of the air column. And you're going to use 331 meters per second unless I give you something different to use for the sound. So for a stringed instrument, you actually have to either be given the speed of the wave on the string, or you have to calculate it using tension, mass, and length. Or for a pipe that's open on both ends, you're just going to use 331 for the speed of sound unless something else is given to you. So if we were going to do an example of this, let's say you have a flute. Here's Lizzo playing James Madison's crystal flute. Much to the dismay of a lot of people, but it's super awesome that she plays the flute because I play the flute too. So the length of it is 0.40 meters, and we want to know the first 3 harmonics. So F1 is NV all over 2L. So 1 times 331 meters per second divided by 2 times 0.40 meters. So if we put that, so that would be 331 divided by 0.8, which is 413 or 414 hertz. F2 is just 2 times F1, which is 828 hertz. F3 is 3 times F1, and 3 would be 2,41242 hertz, and so forth, right? I could keep going forever on that. Other instruments that we see in bands and orchestras have pipes that are closed on one end. So that would be like a tuba trumpet. Okay, these are usually our brass instruments, or a Coke bottle that you're blowing over, right? A Coke bottle. Here's your bottle. It's got one hole in it, and if you blow over it like that, you can actually get that air column to resonate. What's different about it is that when n equals 1, the length of that column is equal to 1/4 of lambda 1. And it turns out that whereas we could go up by integers, 1, 2, 3, 4, it turns out there is no N2 that can form here, because you have to have a node form at the closed end and an antinode form at the open end. So there is no N2 or N4 or N6, but there is an N3 and an N5 and an N7. So what's different about the closed end pipes and adds to the quality is that there's a limited number of frequencies that can occur with a given air column, and they only are the odd numbered harmonics. So only odd numbered harmonics or octaves can form. And the formula that relates that is F equals NV all over 4L, because instead of this going up by multiples of halves, it's going up by multiples of fourths, and it's going up by the odd multiples of the wavelength. And so forth. You can't get a 2 over 4 or a 4 over 4 or a 6 over 4 to form. It won't happen. So, and once again, this is a pipe, so the speed of sound is going to be 331 unless otherwise given to you. So let's do a Coke bottle. So let's say that we know the length is 0.23 meters, so you need to change centimeters to meters. You're just going to blow across the top of it. It doesn't have any liquid in it at all. So the fundamental frequency would be 1 times 331 meters per second divided by 4 times 0.23 meters. So if I do that, 331 divided by the quantity 4 times 0.23 equals 359.7 or 360 hertz. There is no F2, so the next harmonic that will form is F3, which is 3 times F1. And 3 times that would be 0.1080 hertz. There is no F4, so the next one, the next optic that would form is F5, which is 5 times F1, which would be 0.00315 1800 hertz. So just the first 3 odd harmonics will form if the pipe is closed on one end.